In this video we have a look at matrix multiplication and a possible application of this operation. For more videos on matrices and other aspects of mathematics, please subscribe to the You Do the Maths YouTube channel. The first thing to understand is that matrix multiplication is quite different to addition and subtraction of matrices. For the two matrices shown on the screen, we can't actually complete the operation of B multiplied by A, but we can complete the operation of A multiplied by B. For the two matrices shown here, C and D, we can't complete the multiplication of C by D, nor can we do D multiplied by C. Let's have a look at an example of the matrices C and A where we can complete the operation, and we'll have a look at how we decide that this is possible. The first thing to note is the dimensions of both matrices. C has 2 rows and 3 columns, so its dimensions are 2 by 3. A has 3 rows and 2 columns, so it's a 3 by 2 matrix. Let's write those dimensions down for both matrices. C has 2 rows and 3 columns. A has 3 rows and 2 columns. If those inside numbers match, in other words the 2 3's in this case, multiplication is possible. The dimensions of the resulting matrix are based on the remaining numbers. In other words, it's going to be a 2 by 2 matrix. So to perform the operation, what we first of all do is look at row 1 of matrix C, and we match this up to column 1 of matrix A, and this is going to give us the first entry of our new matrix. To perform the calculation, we use the first entry in the first row of matrix C and multiply that by the first entry in the first column of matrix A. We then add this to the product of the second entry in the first row of matrix C by the second entry in the first column of matrix A. And finally we use the third entry in the first row of matrix C and multiply that by the third entry in the first column of matrix A. When we determine these products, we add them together and we get a result of 1. That number goes into our first row of our resulting matrix, which is a 2 by 2 matrix. We now multiply matching entries from the first row of matrix C with the second column of matrix A. This might be a good time to pause to see if you can get the resulting entry of 10. We'll have a look at that immediately after this pause. So our matching pairs to achieve a result of 10 are 1 and 0, and then the second entry in the row of C and the column of A are 4 and 2, and the last entry for C in row 1 is 2, and then 1 in the second column of matrix A. Those products give us a result of 0, 8, and 2, which when combined in addition give us a total of 10, and that goes in the first row and second column of our product matrix. Once we've exhausted all the columns in our second matrix, in this case matrix A, then what we need to do is go to a new row in our first matrix, in this case matrix C. So we're going to multiply all the entries in row 2 of matrix C by the matching entries in the corresponding columns of matrix A. To achieve our next entry, we've circled the relevant row of matrix C and the column, in this case column 1 of matrix A. Doing those multiplications and then a further addition, we get a total of 13 for the first entry in our second row of the product matrix. Let's have a look at how that occurs. Those products are 3 multiplied by 3, 1 by -1, and 5 by 1, and the totals are 9, -1, and 5. When added together, that gives us our total of 13 for the first entry of row 2 of our product matrix. To find the last entry in our new matrix, we multiply the matching entries of row 2 in matrix C by column 2 in matrix A. When we do that, we get a total of 7. That comes about by multiplying 3 by 0, 1 by 2, and 5 by 1. And the results of those multiplications are 0, 2, and 5. And the total when we add them is 7. So that completes our 2 by 2 matrix for C multiplied by A in that order. What happens if we reverse the order and this time multiply A by C? Well, that's likely going to give us a completely different result. For starters, we need to check the dimensions when we multiply in that order. So we need to check our matrices in the order of multiplication. A comes first, and that's a 3 by 2 matrix. C is then a 2 by 3 matrix. The inside numbers match, so we can multiply the matrices. And our result is the outer numbers, which is a 3 by 3 matrix. Our first entry in the new matrix comes about by looking at row 1 of matrix A and column 1 of matrix C. And those multiplications are 3 by 1 added to 0 by 3. Our next entry is the first row of matrix A by the second column of matrix C, which is 3 by 4 added to 0 multiplied by 1. And the last entry in the first row is achieved by multiplying 3 by 2 and 0 by 5, which are the numbers in the first row of matrix A and the last column of matrix C. Those entries come to 3, 12, and 6. Once we've exhausted the columns of the second matrix, in this case matrix C, what we now have to do is go to a new row of our first matrix, in this case matrix A. So now we're multiplying the entries in the second row of matrix A by each of the columns in matrix C. So the first entry in the second row is achieved by multiplying negative 1 by 1 and adding that to the product of 2 and 3. Then the next entry is the product of negative 1 and 4 added to 2 multiplied by 1. And the last entry for the second row will be negative 1 multiplied by 2 and then 2 multiplied by 5. So we're multiplying the entries in row 2 of matrix A by the matching entries in each of the columns of matrix C. Resulting values for row 2 are 5, negative 2, and 8. Once again, we've exhausted the columns of matrix C, so we need to start a new row in matrix A. This time we're multiplying the entries of row 3 in matrix A by the columns of matrix C. So we start with 1 multiplied by 1 added to the product of 1 and 3. Then we have 1 multiplied by 4 added to 1 multiplied by 1. And then we have the product of 1 and 2 added to 1 multiplied by 5. So the resulting entries for row 3 are 4, 5, and 7. That completes the calculation of the matrix multiplication of A by C in that order. It's significant to note that we not only get very different values, but we also get a different size matrix compared to the original example where we multiplied C by A and achieved a 2 by 2 matrix. Let's have a look at a different example now, multiplying matrix A by another matrix, in this case matrix B, which is a 2 by 2 matrix. As with any matrix multiplication, the first thing to do is to note the dimensions of both matrices. So matrix A is a 3 by 2 matrix, 3 rows, 2 columns. Matrix B is a 2 by 2. Those inside numbers which we've underlined do match, and the resulting dimensions of our new matrix are the remaining numbers, in other words a 3 by 2 matrix. We'll do this example a little bit quicker, so you may wish to pause the video at certain stages to check to see that you agree with the resulting entries. So using the first row of matrix A and the first column of matrix B, we get 3 multiplied by 4 and 0 multiplied by 0 to give us a total of 12. We then multiply 3 by negative 1 and 0 by 2 to give us a total of negative 3. We've exhausted the columns in matrix B, so now we need a new row in matrix A. Negative 1 multiplied by 4 and 2 multiplied by 0 gives us negative 4. We go to the second column of matrix B and we get negative 1 by negative 1 and 2 by 2 to give us a total of 5. Again, we've used the columns in matrix B, so now we move to a new row of matrix A. 1 multiplied by 4 added to 1 multiplied by 0 gives us 4 for the start of our third row of the new matrix. For the final entry, we multiply 1 by negative 1 and add that to the product of 1 and 2 to get a total of 1 for the last entry in the new matrix of A multiplied by B. So what if we reverse the order and this time multiply B by A? Let's have a look at what happens when we try to achieve this product. We know that matrix B is a 2 by 2 matrix. We also know that matrix A is a 3 by 2 matrix. when we look at the inside numbers of those dimensions which we've underlined, they don't match. That means that we can't complete this matrix multiplication. It's not possible. For our solution, we can write down that this product cannot be determined, and we can express that by saying the number of columns in B does not match the number of rows in A. Let's have a look at a possible application of matrix multiplication. Here we have a matrix that represents different costs for aspects of holidays to different locations around Australia. So we have 3 locations expressed at the top of the matrix, that's Perth, Broome and Albany, and then the costs for different types of activities on the holiday. So that's eating or food costs, accommodation and travel. So these costs are based on costs per day. Then what we do is we have a matrix that represents the number of days that we stay at each of the locations. We can see that expressed as a column matrix T. So if we want to work out costs of different aspects of our holiday, we can start by looking at food costs and say for Perth, $80 a day for 10 days is a total cost of 80 multiplied by 10. For Broome, the food costs are 90 multiplied by 5, in other words $90 for 5 days. And for Albany, it's $70 for 6 days, or 70 multiplied by 6. This gives us a total food cost of $1,670. But is there a more efficient way to achieve this using matrix multiplication? Looking at our 2 matrices, we can see that H is a 3 by 3 matrix, 3 rows and 3 columns, and T is a 3 by 1 matrix, 3 rows and just 1 column. In other words, T is a column matrix. And if we look at the inside numbers, so to speak, of the product of H multiplied by T, we can see that they match. H has got 3 columns, T has got 3 rows. So we can perform a matrix multiplication of H by T to achieve a 3 by 1 matrix. When we do that, we get a matrix that gives us all the costs for the different aspects of our holiday in one column. This is just one example of the use of matrix multiplication. There are many others in mathematics, including transformations and solving systems of linear equations, just to name a few.